But did it damp down the echoes?
No, but
Made them louder. Yeah, okay.
One carpeted room, which was all soft, squishy walls and just spongy carpet.
And that one was not very. Yeah. These things are crazy. Right now, when I'm talking to you now, you can hear me. Why can you hear me now so well? Is the sound coming through the back of my head? No, I feel the back of my head. It is not shaking very much. I can feel a little bit. Right? Is it reflecting off of this? Do you suppose? Right? In an anechoic room, what the tour guide does, I've been in one of these things, this is the shtick. You walk out there, right? This little expanded metal thing doesn't reflect much sound, right? They walk out there and they just turn their head away from you. And you can just barely hear them. When they turn their head away from you, none of the sound reflects off the walls. You can't hear them. And it's like, aha. All right. There's a 50-50 chance I'm setting this up correctly. What do you think? Do you think this is going to reflect if I hook these guys up? Oh, this one's got shorter bars on it. Is the wave going to travel faster or slower? Everybody says faster because it's got less inertia, correct? But it's got the same spring in the middle. That would have been the other question you might want to have asked. Right? It does have the same springiness, but it's got more mass. Now, is there going to be a reflection off of that? Yeah, this is what we would call an abrupt change in medium. So watch. It's like I send an up pulse, comes back as a... Do you see the reflection right off of that, right away? Yeah. Watch. Up pulse. See the reflection? There's a transmitted wave. There's also a reflection. So this is light traveling through air. Goes very fast. Travels through glass more slowly. Right? So there's a reflection off of there. Now watch. If I send an up pulse, we get back a down pulse, yes? So this is acting like what? A fixed end or a free end? It's fixed. It's not totally fixed, but it's more fixed, correct? It's got more inertia, right? It's more like a fixed end than a free end, right? So it's this thing, right? I send an up pulse, we get back a down pulse. And there's also a fair amount transmitted. And then it reflects off the end and all this stuff, right? How about the other way? Is this going to be a fixed end to it or a free end?
Free.
Fixed or free?
Free.
Let's try it. It's got less inertia, right? Let's just try it. Up pulse sent down. Watch the reflection. Little up pulse, yeah? So this is freer than this because it has less inertia, right? Right. So this acts like a free end to it. It's a little bit crazy, huh? So, so what would an impedance transformer look like for this? What would it look like?
It'd be like gradually bigger.
Gradually getting bigger. Do you suppose I have one of those? There's a reason. Now here's the 50-50 thing, right? Did I set it up right? No! Fail. All right. Wanna bagush. Well, no, that's not the difficulty here. Okay, so. Dun, dun, da, da, dun, dun, da, da. Is this going to help it? It might. Yes, there we go. All right. Being very careful not to bend these guys. We've actually broken these and had to JB weld them. All right, let's go out over the sink. You guys see, I would feel bad if you guys didn't get all $600 worth of this thing. Right? Stay. I was about to fail, but now I am ready for success. Et voila! Huh? This is called a wave device impedance transformer. I'd like to buy a vowel. Okay. That's a Canadian joke. All right. This is sad. You guys are, each of you, getting about 10 cents worth of learning out of this, but that adds up, right? Over the years, We've more than made back our $600 investment. Like, all of this to... So do you suppose it's a bad thing on a telescope that the light sometimes reflects off the glass when you're trying to collect light? Yeah, so what they do is they actually put coatings on the glass. And this is, if you are a material scientist, this is like big, big stuff, right? What they do is they put coatings on the glass so that light traveling from space, when it enters the glass, has to slow down, right? And so what they do is they put a coating on the glass, and it's very, very thin. But what it does is it gradually makes that change. And so more light gets into the telescope. And so, and I don't remember who it is, but there's Meade and there's Celestron or something like that, right? And they've each got their own recipe. And one of them claims that their telescopes, if they've got a 10-inch telescope, that's the size, that their 10-inch telescopes are better than the other person's 10-inch telescope because the coating is better. Yeah? So this is the difference between a cheap telescope and a little more expensive telescope. Are you guys dying to see this in action? Watch. Ooh, hardly any reflection. Only there's still a little bit of a reflection, right? It's like, whoa, that's kind of cool, isn't it? Let's give that some applause. Like,
do they have like impedance transformers for like your eyes, like sunglasses?
yeah, they've got basically the sunglasses. They're trying to reflect a lot of it, right? They don't want the light to get in there, so they make them purposely like you know, a reflecting coating, right? And then, but yeah, I mean, they could make something that, like, obviously those ones that they're trying to amplify the light. They probably put coatings on those, right? Okay, and then the final thing that I'll leave you guys with. You guys are like, class is over. No, it's not quite over, right? The final thing I'll leave you with is that there's something, you know, we talk about angle of incidence, angle of reflection, right? Okay, and you can have some fun with this. But if these angles are equal, like that, if you send a beam of light into a corner, right, if this thing makes a 90-degree corner, a beam of light coming in is actually going to come out along the path that it entered in, right? And so I've got this mirror here, and when you look in this mirror, you actually see your face. Go ahead and touch the right side of your face. Yeah, here we go. It's like, this is a non-inverting mirror, and so when I touch my side of my face like this, I see the person in the mirror put their hand on, well, their right side of their face, right? But it's inverted or something like that, right? Now, the cool thing about this is that if we hold it, and you can hold that and point the corner at me, right? If I send a laser beam into this, and it's three-dimensional, where's it going to go? All right, here we go. Hold it above your head. All right, there we go. Let's turn this on. Zoom! Just kidding. Is it on? Oh, there we go. All right, tip it down a little bit. This is, by the way, moderately more powerful than a pocket laser pointer. Where's it going? Tip it down a little bit. Yeah, there you go. It's like going to blind me. It's like, oh, there, I got my eye. Oh, here we go. Yeah, there you go.
Where's it pointing at?
There you go. So these things, when you look at surveyors, they actually use these. These things are called prisms. You can send a laser beam into them, and the laser beam comes right back along that path.